present Andrey Lunkov, our speaker of today. Andrey is a senior scientist in the hydrophysical laboratory in the Russian Academy of Science. Andrey completed his master's degree at the Bauman Moscow State Technical University and his PhD at Prokhorov General Physics Institute at the Russian Academy of Science. And his main scientific interests are shallow and water acoustics and acoustic oceanography. Please.
Okay, thank you, Regina. So, let's start. Good afternoon, ladies and gentlemen, dear colleagues. It's my pleasure to be at the University of Haifa again. This is my third visit to Leon Charmy School of Marine Sciences, and I decided to share with you some of the results of my research in cooperation with Boris Katsindeson, Regina Katzman, and Ilya Ostrovsky. My talk today is about sound propagation in shallow water with gassy sediments. So a few more details about my scientific interests. So my interests are sound propagation in a time-varying environment. I mean sound propagation in the presence of surface waves or internal waves. Also, it's time reversal focusing of acoustic waves and monitoring of hydrodynamic processes by means of acoustical interferometry and bottom characterization by analyzing multiple sound reflections. So our joint study together with Regina, Boris and Ilya is now focused on bottom characterization of Lake Kinneret by acoustical means. Let me remind you something about sound propagation in a medium. So the basic characteristic of sound propagation in a medium is the speed of sound. So the speed of sound is the distance traveled by acoustic wave per unit time. And for a liquid medium or for a gas, we can derive the following formula for the sound speed. Here you can see capital K is the bulk modulus or Young's modulus, rho is the density, and sometimes it is convenient to represent the sound speed in terms of compressibility, beta. So here you can see different values for sound speed in different media. For example, in the air, I think you know that the sound speed is 331 meters per second. In the water, it's about 1500, and in rigid materials like granite, it's about 5000 meters per second, and in shaving foam, the sound speed is about 50 meters per second. This value is due to very high compressibility of the shaving foam. So let's consider sound propagation in shallow water environment. Shallow water is the natural waveguide for acoustic waves. We have two boundaries, upper boundary between water and air, and lower boundary between water column and lake bottom. So upper boundary is almost perfect reflector for acoustic waves. So let's take a point sound source and a single hydrophone. Sound radiated by a sound source can reach our hydrophone along different paths or rays. The first one is the shortest one, it's the straight ray. Later, two rays with one reflection from either upper or lower boundary go, and after that we have two rays with two reflections, and so on, and so on. And if a short pulse is radiated by a sound source, the following structure of received signal will be observed. You can see the maximums corresponding to arrivals of sound signals along different paths. For example, this one corresponds to the signal along this path, the second one along this path, and so on and so on. And as I told you, the surface is the sea surface or shallow water surface is almost perfect reflector, and the bottom usually is not a perfect reflector. So the amplitudes of these arrivals will depend greatly on characteristics of, in our case, lake bottom. So it is easy to estimate sound speed in water using direct measurements, just to know the time and know the distance between 2 points, between sound and receiver. And it is more difficult task to estimate the sound speed in sediments, because it's difficult to dig and to put into sediments sound sources and receivers. So next, let's consider the interaction of acoustic waves with bottom in more detail. Generally, there are two possible scenarios. The first one is the scenario of rigid bottom, when the sound speed in the bottom is higher than in the water. So I should say that here the homogeneous sediment layer is assumed. So, and another scenario is soft bottom, when sound speed in the bottom is less than in water. So this scenario is typical for ocean environments, and this scenario is typical for shallow water environment. I mean, for example, fresh water lakes or some reservoirs. So what is the difference between these two scenarios? The difference reveals in the dependence of reflection coefficient of the acoustic waves on grazing angle. The grazing angle is an angle between the incident ray and the boundary between water and sediment. So in the first case, we have a so-called critical angle. Below this angle, almost all energy comes back into the waveguide. And if we have the second scenario, we have no such an angle, and at any angle, at any grazing angle, energy will penetrate in the bottom. So what could be the reason of low sound speed in sediments? The reason is the presence of gas fraction or maybe gas bubbles. So, and if we take a following model, a three-component media consisted of rigid particles, water, and gas bubbles, we can estimate the effective sound speed in this media in connection with the gas fraction. And as you can see, if we have 1% of gas fraction, the sound speed is about 100 meters per second. So it's lower than the sound speed even in the air. So, and sound speed is very sensitive to the presence of gas, and we can use estimation of effective sound speed to evaluate the amount of gas in sediments. So several methods for estimating the gas fraction using acoustical means were considered in the master thesis of Itzhak Elhanati, high resolution seismic characterization of shallow Burin sediments. This work was done also for Lake Kinneret, but for, as I know, for shallow regions when the depth is no more than maybe 15 meters. So we propose a similar technique, but I mean in terms of acoustics. But we propose to use multiple reflections, like you see this, and to analyze the decay of reflection amplitudes to estimate the effective sound speed. So we conducted 3 experiments in Lake Kinneret this year. They were in February, April, and May. Our main purposes was to study the long-range underwater sound propagation and to estimate the effective sediment parameters. Here you can see the bathymetry map of Lake Kinneret. White dashed line denotes the transect along which we conducted most of our experiments, and the white star denotes the position of the central station in Lake Kinneret. Here is situated a special platform. This platform is stationary and it is called EcoRaft. So you can deploy, for example, acoustical equipment or something else from this EcoRaft. Also, were entered 2 research vessels. It was research vessel Lilian and research vessel Hermona. We used 1 research vessel in 1 experiment. So, and some words about our acoustical equipment that we used. Here you can see the broadband underwater acoustic transducer, and we also used 2 low-noise broadband hydrophones. So the sound source was deployed from either Lilian or Hermona, and sound receivers or hydrophones were deployed from EcoRaft, so research vessel Hermona. So, and some words about the radiated signals in experiments. The chirp signals were radiated. The chirp signal is the signal with increasing frequency. So here is the example of the chirp signal. Here we have the frequency of 200 Hertz, and here we have the frequency of 2000 Hertz. And the frequency is changing smoothly in time. So the duration of our transmission cycles was 5 seconds. So it is common to use correlation processing of chirp signals to get a short pulse, and such correlation processing was applied to all the signals recorded in our experiments. So, and let's talk about local measurements that we conducted. Here you can see the results of our measurements when sound source and sound receiver were close to each other. The range between them was just from 3 to 5 meters, and the source depth was 6 meters and the receiver depth was 5 meters. And we conducted our measurements in many locations with different depth of the water column. So here you can see the pulse structure of the received signal, and we can observe that at low depth, when the depth, for example, is 11 meters, we have not so many rails, just a few rails. And if we increase our depth, we have more and more arrivals, and these arrivals were processed to obtain the effective sound speed in sediments. And after that, we estimated the gas fraction in this sediments. So, and something about our technique for estimating sound speed. We used so-called match field processing of the received signal. So we compared the amplitudes of each arrival obtained in experiment and in simulations. We used numerical simulations of the sound field. So here you can see the comparison of simulated, it's red lines, data and experimental data. If we take the sediment with low sound speed, we have many reflections, that's red peaks. And in experiments we had not so many peaks. So it's this sound speed is too low for our case. So if we take, for example, 700 meters per second, we have less peaks than in experiments. So it is also not true. So the best agreement was obtained for the case when the sound speed in sediments is about 400 meters per second. You can see the good agreement between peaks in simulation and experiment. So the results of our estimation are presented in this slide for different locations with different depth. And the overall trend was the increase was the decrease of the effective sound speed with depth. It means that the gas fraction becomes higher and higher with depth. So here you can see the dependence of the effective sound speed in sediments on the water depth. So the blue line is for sound speed, the green line is for the gas fraction. So the gas fraction was calculated using this dependence. For example, if we have the sound speed of 400 meters, here we have 2 multiplied by 10 to minus 4 gas fraction. So, as you can see, at first, when the depth is changing from 11 to 15 meters, the strong increase in gas fraction is observed. Then the small decay, we can see the small decay, and after that the gas fraction is growing again. So, and it was interesting to compare our results with the known data from already published papers. So the gas fraction is an evidence of organic materials that produce the gas bubbles. And here you can see the dependencies of organic material concentration on depth, and this is the dependence of proportion of sand, seal, and clay on also the depth. These are the results of in situ local measurements using just pores of sediments. We were surprised to find out a good agreement between the previously published data, and you can see that between the depth of 10 and 15 meters, the strong increase in silt concentration is observed, and organic material is also greatly increased. And we have the same situation in our measurements. So after that, we have authors of this paper had a slow decay of silt concentration and organic material concentration, and we also had this small decrease. And after that, everything is growing. So it's our preliminary results. These results were obtained just last Tuesday, so maybe we'll do some corrections and we'll conduct more detailed investigation. So, but these results, I think, are reasonable and promising. So now I would like to talk about acoustic pulse propagation at long ranges. In addition to local measurements of acoustic fields, we conducted long-range measurements. So we deployed one or two hydrophones from EcoRaft, and the sound source was carried by either ship, either research vessel, either Hermona or Lilia. So, and we received signals from different ranges from a few meters to 6 kilometers. So here you can see the structure of arrivals at different ranges. Here you can see the closest range, and here is the furthest range. And as you can see, the number of arrivals increases with range. And after some range, the arrivals start to group in the so-called waveguide modes. So here we start to see the groups of rays forming a so-called waveguide modes. Waveguide modes are the common representation of the sound field in underwater acoustics, or just in waveguide acoustics. So if we perform the short time Fourier transform, or we take spectrogram of these dependencies, we can obtain the following time frequency structure of arrivals. So horizontal is time and vertical is frequency in hertz. So at the closest range we have only vertical stripes, and after that these stripes start to look like some spotted stripes here, and after that these spots start to align along hyperbolas. The hyperbolas are the evidence of the waveguide modes. So at the farthest distance we see only hyperbolas. So there are only waveguide modes, but not the rays. So the similar results were obtained in April 30. This was the results of February 2nd, and this is the results of April 30. So we can see the similar situation, but the structure is more smashed due to the peculiarities of sound speed or temperature profile in water. Because in winter conditions the sound speed was constant along the whole water column, and in spring we have a so-called thermocline near the surface with warm water, and below this we have just cold water. So, and the structure of arrivals becomes different. So, and my summary: first, a series of experiments were conducted in Lake Kinneret to study mid-frequency underwater sound propagation. And it is important that coherent wideband signals were applied. Coherent, I mean the signals with a good repeatability and stability. So this is no explosions and so on. So the second point is effective sound speed in the upper sedimentary layer was estimated at several points with different depth. Preliminary data processing has shown that gas concentration in the center of the lake may be higher than near shore. And the third one, purely acoustical one, is that during studying long range up to 6 kilometers sound propagation, it was observed a continuous transition of acoustic rays to waveguide mode. So, and some words about our future work. We are going to improve our technique to estimate bottom parameters by including multiple layers, and to analyze nonlinear effect associated with acoustic wave interaction with gas bubbles. And the second big goal is to arrange a stationary acoustic track in the Lake Kinneret to study the long period internal Kelvin and Poincaré waves. I should say that preliminary numerical simulations have already been done by me and Boris, and we want to verify our numerical results in the experiment. So that's my talk. Thank you for attention.
Thank you very much, Andrey. Any questions, please?
Yes, several questions. First of all, it's a very nice work. Can you, one question, when you do the estimation of velocities, what do you think is the thickness of the layer that you're estimating? What is the integral that you're doing?
I think the thickness is the wavelength of acoustic waves. So
which
it's about no more than half a meter.
Half a meter?
Half a meter, yes.
So it's low frequency.
No.
What was the frequency that you used?
1 kilohertz.
1 kilohertz, okay.
Yeah.
So it's about half a meter.
Half a meter, no more.
No more, not much less either.
Maybe less, a bit less, because the wavelengths in water, for example, at the frequency of 1 kilohertz, is 1.5 meters. But if you have a media with a low sound speed, in our case it's 300 meters per second, the wavelengths will decrease by 5 times. So the wavelengths will be just 30 centimeters.
Okay, can you show again the fit to the fit to the curves? I see one pulse in every repetition, when in your situation you should get the pulse from above and pulse from below.
Yes.
You distinguish between them?
No, this one, of course, this one is the straight ray, just this straight pulse. This pulse is reflected from the up, and this is from what?
This is down, this is up, down,
Yeah.
Okay.
Up, down, 2 reflections, 3 reflections, and so on and so on.
Okay. Can you also show the spectrum, the last one? Finally, I understand how I go from reflection seismology to wave mode, which is great. Can you explain why is the loss of the low frequencies?
Because the peculiarity of our radiated signal. Because
Saying it's
the
the
amplitude.
correlation that changes.
No. The problem is the amplitude. The sound source can give the low amplitude at lower frequencies. And to radiate low frequencies, we need big sources. So, for example, if we want to radiate 100 hertz, we need a sound source looks like this. But we have a smaller one.
Oh yeah, or yeah, definitely. Okay, so it's the peculiar. Did you when you did the deconvolution? Did you do the deconvolution assuming the original signature?
Yeah, sure.
You didn't consider the change of the wavelet with all these reflectivities, because the deconvolution operator should change with time.
No. We just make deconvolution with the radiated signal. So we did not change.
This may be something to check. Because what happens is that if you are losing frequency and you are changing, you're also changing phase. Slowly, your deconvolution should change. Because you're doing such a precise and nice work, maybe you should consider locally evaluating the deconvolution. Okay. Yeah, that might improve a little bit here. But great, beautiful work.
Nice.
Yeah, definitely. Finally, I understand.
Any other questions?
For 3 years, I wait until you explain me this. Nice.
Okay.
So maybe for students, it will be interesting where we implement short time Fourier transform to get spectrograms. So here you can see the spectrograms.
I want this slide.
No problem.
Just for teaching purpose.
Okay.
Finally, I understand.
Okay.
More questions?
I told.
Okay, thank you very much.
I told
Andrey,
about
for your
this
talk.
lecture. Just from teaching.
This is protected. Definitely. Finally, I understand. David. You have 3 words about 10 meters.